is just not increasing nearly as quickly as it did when I was growing up. We bought a new machine every 2 years, and it blew the old one completely out of the water. And so I went and I looked for some statistics to back that up, and I found a few. The first one there is from somebody's blog post, and he went and looked at single-threaded SpecInt and SpecFT benchmarks, which is kind of a funny concept because there's like implicit parallelism stuff going on there. But he did his best to separate it out and found that between 96 and 04, he saw performance increasing by more than 50% year over year, which is a less than 2-year doubling time. But between 2004 and 2012, he saw it increasing pretty steadily at 21% a year. Now, I personally would be pretty happy if all my things got 20% faster every year, but it is definitely a slowing of the rate that we used to see. And I think on a lot of real-world tests, you actually see less gain than that. And so another example that I found was from the Advantech website. They did some benchmarks when they upgraded their web server. Only one of those was a single-threaded benchmark, which right there tells you something about why we need parallelism. But the single-threaded benchmark, I worked it out. It's an annualized rate of 7.7% per year based on the date those CPUs were initially released. 39% improvement over roughly 4.5 years. So if your data is growing faster than that, and you're stuck in this single-threaded world, then you're getting slower with every year that passes by. I think the most compelling evidence I found of this trend is, we sometimes tell people, or at least I sometimes tell people when they're betting on PostgreSQL servers, don't buy more cores, buy faster cores. But I went to the Dell, and it's good advice up to a point, but there's a growing problem in this area. I went to the Dell configuration tool, which I've always found to be a really great way of putting a machine together and understanding how much the components will cost. And on their high-end servers, you got these two processor options, one at 2.8 gigahertz, one at 3.4 gigahertz, overall fairly similar. At 3.4 gigahertz, you're paying $8,400 instead of $7,700, but that's okay because it's faster. What's not so okay is that you've got 6 cores on the more expensive one with the higher clock speed and 15 cores on the lower speed one. And that's something where a lot of people are either going to make the wrong decision or just say, that's crazy. You can't expect me to pay that much more for my hardware if I want to run PostgreSQL. And really, how far out of the problem are you going to get by having a 3.4 gigahertz processor rather than a 2.8 gigahertz processor? That's just not enough of a difference, especially when you consider that the memory interconnect is the same speed. To really get out from under this problem. And I want to add here that I'm primarily concerned with things that take minutes or hours to run. If your query runs in a couple of seconds and you want it to run in fewer seconds, that's probably a problem that's worth solving, but it's not really the use case that I'm concerned with here, at least not at first. I think it'd be useful also to just do a brief overview of what kinds of things we might be able to parallelize in PostgreSQL. In thinking over this, I think there are kind of 3 main categories, 2 related to queries, and then one other group. So this is a plan that looks vaguely like something that might come out of Explain. We've got a sequential scan on foo, and then we're doing a hash join against bar. So we scan bar and build a hash table, and then we do a hash join between the two. So a simple plan. But imagine that the foo table is really, really big, so that this hash join is going to take a long time to run. What can we do to make it faster? Well, one thing we can think about doing is pipelining the execution of these 2 operations. You've got a hash join and you've got a sequential scan. So why not have one process do the sequential scan and the other process do the hash join and feed tuples from one to the other? So this is what I'm calling inter-node parallelism, because it's parallelism between one node and another node, right? You do some nodes over here and you do some nodes over there and they talk to each other, right? Now the other way of looking at this same plan tree is, maybe we need more than 2 processes working on this plan tree. In that case, we need to actually do parallelism within single nodes, or intra-node parallelism. So sequential scans, for example, I'm supposing that we have a filter condition here, which is the well-known something complicated filter condition, which, as you guys all know, takes a lot of CPU time in order to execute because it's so complicated. So we might not be I/O bound doing that sequential scan on table food. We might actually be CPU bound. And if we are, or our database might fit in memory, which when you can get a commodity server with a terabyte of memory does not strain credulity too much. We might like to actually have multiple backends processing this foo relation. Different backends process different blocks. Each backend applies the filter condition and the MPCC visibility checks to its own block and passes the results up to the join. And hey, while we're at it, maybe we could parallelize the join, right? I mean, if we've got multiple streams of tuples coming in from somewhere, and we parcel those out to a series of backends that have access to a shared hash table that we built over the bar relation, each of those guys can do independent probes into that shared hash table and do part of the hash join separately. We don't even need locking on the hash table because it's not changing once it's initially built. So there's a lot of interesting things that could be done here, and none of them work yet. The third category, moving outside the realm of parallel query, is parallel maintenance or DDL commands. I think these may actually be good early candidates for parallelism for two reasons. One is that it's easier, and this is a really hard project, so anything that's even a little bit easier is always nice. And two is, some of this stuff takes a really long time. That, I think, is the case where you can get the most win from parallelism. So I'm thinking about things like create index, where, again, you could perhaps parallelize the heap scan, you could perhaps parallelize the sort if we need to put the data in the right order. Or vacuum. Again, obviously, parallelizing the heap scan could be a very useful thing to do. I was having dinner with Andres and Nikki the other night, and they were pointing out that once you finish the first scan through the heap, you have to go and scan all of the indexes, however many of them there may be, and remove the tuples that you've identified as dead from each of those indexes. Well, right now, we do that one index, and then the next index, and then the next index, however many indexes there are. If you've got one index on your primary key, that's one thing, but if you've got 10 indexes on the table, which people sometimes do, there's a really obvious opportunity for parallelism there by having different workers scan different indexes. Now, maybe you could even make it more fine-grained than that and have multiple workers who operate on a single index. But even just getting to one worker per index would help people who have indexed the heck out of their tables. So those are some of the kinds of things we can probably parallelize. I'll just pause briefly here and ask if anyone wants to ask a question before I move on to technical ramblings. Yeah?
How are you balancing out the trade-off? Like the 7-zip example, that's a single application doing a single job. Okay,
Yeah.
one connection to a database, I've got hundreds of connections doing hundreds of things. Each one of those is executing its own stack, its own execution thread. If I introduce parallelism there, am I introducing contention for CPUs that wasn't there before?
Right.
I might be speeding up a single query.
Right.
I might be slowing down other things.
This is something I was going to allude to later. The question is basically, if all my CPUs are already in use, and then I start doing parallelism at whatever time, I might actually be making things worse for the system overall, even if performance for one particular process gets better. And his question is, so what are you doing about that? And my answer to that is, I'm not doing anything about that yet, because I haven't got that far. But it is a really good thing. It is a really good question. I'll allude to it briefly a little bit later on. Yeah.
This one easy one to add to this list is maintenance commands that hold an exclusive lock on a table like cluster or vacuum flow.
Right, so we're talking about cluster and vacuum flow. You know, cluster in some ways and vacuum flow are in some ways very similar to these commands because once again you have the same opportunities for parallelizing heap scans and sorting. The issues are a little bit different in every case, but yeah, I think once we get the ability to parallelize some of these common operations, we'll then probably go through a period where we try to apply plumb that infrastructure into various different parts of the system, which will no doubt be a barrel of laughs. All right, so I want to talk a little bit about architecture. And some of the architectural decisions that I made early in the project. I obviously am not saying that I've made those decisions for the project, because as much as I might wish that I had that power, I totally don't. I'm talking about the decisions that I made in terms of what I was going to work on and how I was going to pursue this. So if people disagree with these decisions, that would be great to hear about. Maybe after the talk would be better than during the talk, just in the interest of time. I didn't bring any kind of shielding device, so if people feel the urge to throw things at me when they hear some of these things go by, I would sure appreciate if that could be something that you would refrain from. The first decision I made is we're going to use processes, or at least I'm going to try to use processes for this, not for credits. So people often say, oh, you know, it would be so much easier for you to do parallelism if you were using a threaded model than a processed model. And they might be right, because there are certainly plenty of challenges doing it this way. But I don't really feel like rewriting the entire backend and having it become totally unstable and not work anymore. So I just can't see that there's any joy there. I mean, if you start multiple threads inside an individual Postgres backend, the good news is the rest of the system, all the stuff that's in shared memory, doesn't have to know. The bad news is almost every piece of backend local code and every backend local data structure has to know. And there are actually a lot more of those than there are things in shared memory. So changing all of that around, we could have a great argument over alcohol about whether that is a good thing to do on general principle, but I came rapidly to the conclusion, I think it took about 6 microseconds, that if I embarked on that approach with this project, I would be dooming it to certain failure. So I decided to pick the approach that was highly likely to fail rather than the one that was absolutely certain to fail. The second decision that I made, at least for myself, is that I was going to pursue the idea of doing parallelism with processes that were started by the postmaster rather than having individual backends fork to make a bunch of siblings that would then all cooperate on the query. One of the big reasons for that is that we have a lot of users on Windows, and as much as I hate Windows, and I really do, we would not, PostgreSQL as a project would not enjoy the success that we have today if we didn't support Windows as a platform. And I'm not excited to be the first guy who implements a major feature that can never work on Windows under any circumstances whatsoever, and virtually none of the code that we use for that feature on other systems could ever be adopted to work on Windows. I just don't want to be that guy. The other issue, of course, is that right now, today, all backends are direct children of the postmaster. Linux does, and Unix systems in general, don't really handle grandchildren the same way that they handle children. And that's what we would end up with if we tried to have individual processes fork. I'm not saying those issues couldn't be fixed, because they probably could be, but it just felt painful. I think that's a lesser consideration than the fact that it would just completely break on Windows, but it was another thing that leaned me in that direction. All right, so that's the process model. Then what about IPC? How do things communicate with each other? Well, you know, there's a lot of IPC tools available on the platforms that we support. There's relatively few of them that work on every platform we support, which is kind of hits. But pretty much every system has some way of doing shared memory, some way of doing pipes, and of course everybody's got files. Of course, if you're on Windows, the API calls are all different, but you know, never mind. So I kind of rejected files pretty quickly. There might be something we want to use files for within this set of things around parallelism, parallel tape sort or something, but for the most do in terms of streaming data between one process and another process for which pipes would be a good fit. But shared memory is a lot more flexible. And as evidence of that, I offer the fact that you can much more easily use shared memory to emulate a pipe than you can use a pipe to emulate shared memory. Now, Noah pointed out to me that there actually probably are ways to use pipes to emulate shared memory, but I was a little scared of some of those things because some of them were operating system dependent. So what I did instead is I wrote a module called shim_MQ. It uses shared memory to emulate a pipe. And one of the things that I think is nice about that is I've got one set of platform dependencies around shared memory instead of two sets, one around shared memory and one around pipes. And that shim_MQ module actually provides some nice semantics. You can make your pipe as big as you want it to be or as little as you can get away with, depending on what performance characteristics you need. It's totally platform independent. It never splits up messages into smaller messages, which operating facilities would probably do on some platforms and not others. That seems to be working out kind of nicely. I also decided that we needed specifically dynamic shared memory rather than the main shared memory segment. And the big consideration here is that if you want to do a parallel sort, and you want to do like a giant quick sort in memory, you might need like a terabyte of memory. And you can't pre-reserve a terabyte in the main shared memory segment on any system that I'm aware of and not have users complain about the fact that when you're not doing a parallel sort, you're like not using 1 terabyte of their RAM. So that just didn't seem like there was any way to make that work. A more painful decision, and this one was really painful, and the pain will no doubt be with us for a long time, is that we would live with the fact that these dynamic shared memory segments could be mapped at different addresses in different cooperating processes. And that kind of sucks, because it means you can't use absolute pointers inside these dynamic shared memory segments and have things work the way you want them to. I hate that. It's awful. On the other hand, only one hacker has told me that he thinks that it might be possible to actually make having it at the same address in every process, and every other hacker I've talked to, including me when I talk to myself, has said that that is never going to be reliable and it's not going to work and you'll die if you try. So I'm trying to deal with that complexity in individual users of the dynamic shared memory facility rather than baking it into the facility itself. So those are some architectural decisions that I've made.
How did dynamic shared memory differ from shared memory itself? What's the difference between dynamic and shared memory?
Right. So we have so the question was, what's the difference between dynamic shared memory and regular shared memory? There is a regular shared memory segment that we create at Postmaster Startup, and we actually do manage to get that at the same address in every process. On Unix, we do that by forking. On Windows, there's something that kind of
That's not 100% reliable.
and it's not 100% reliable. But we do it, right? Dynamic shared memory segments are different because you can spin up a dynamic shared memory segment anytime you want during the execution of the server. So the main shared memory segment is created once at startup, and that's what you got forever. Dynamic shared memory segments, you can start them up, you can create them on the fly, and you can turn them down while the server is running. And there's no limitations that it has to be a back-end startup or anything like that. Just whenever you want to spin one up, spin one up. When you don't want it anymore, throw it out. Other questions on the architecture stuff?
It promises some benefits.
So the question is about non-uniform memory access. Right now, there's no code at all anywhere in PostgreSQL, which is NUMA aware. There might be a good argument for making some part of the code NUMA aware. What we lack is benchmark results showing that the lack of NUMA awareness is actually hurting us. I don't necessarily doubt that it is, but it's one thing to think that there might be a problem with something, and another thing to have real reproducible test cases that demonstrate that you do have a problem with something. The closest I'm aware of it comes, Kevin benchmark that did show a significant overhead on one workload, but I think you were never able to reproduce that reliably.
Yeah, the results with NUMA are surprisingly unstable from one benchmark to the next, but I've consistently gotten a 1 to 2% improvement by interleaving shared memory for both the main segment and the OS buffers, and occasionally seen differences as high as 20%.
Yeah. So there may well be smarter things that we can do there, but I think we just don't have to be that smart. I don't think this particular project is the right place to start having that smarts. If there's smarts to be added, it's probably much more useful to add them to the existing stuff that everybody uses all the time. Yeah.
Can I safely assume that the dynamic shared memory uses the same sidestep that you made in 9.3 to get around the small smacks problem?
Right, so the question is, can we safely assume that dynamic shared memory uses the same sidestep around the System 5 shared memory issue that I added in 9.3? The answer is no, you can't assume that because it's completely false. The trick we used in that case does not work for this case because the only way of propagating that kind of shared memory segment from one process to another is via fork, which is not an option here. So what we have for dynamic shared memory is a configuration variable that lets you pick from among the shared memory implementations that work on your operating system. Hopefully most people will have POSIX shared memory, which doesn't suffer from the System 5 limits, but if you're running on a BSD system, you might find that you haven't got POSIX shared memory, in which case you should, number one, ask your BSD kernel guys very nicely if they wouldn't mind adding that, and number two, configure the variable to point to say System 5. NNDB will actually take care of it for you. I'm going to move on here, just in the interest of time, because I think people will have questions about some of the later slides as well. So the basic question here is, what do we need to build, and how far along are we in building it in terms of actually making something that works, as opposed to something you can give a conference talk about. I've kind of divided the work here into 5 areas, and the parenthesized comments give you some idea of where we are with those areas. There's some basic facilities, which I think are pretty much done in line 4, that are sort of the very fundamental building blocks of parallelism. Then there's what I'm calling plumbing, which is a bunch of things that are not technically part of those basic facilities, but are actually needed in order to use them in an effective way. I'll talk a little bit more about each of these over the coming slides, so don't get too hung up if you don't totally understand what I'm saying now. Then the next thing is establishing what I'm calling a parallel environment. I'll talk a little bit more about what that means. Internally at EDB, we've done a little hacking on this. We've got some ideas. There's a lot more work to be done there. And then once you have this parallel environment, the goal of the parallel environment on top of the plumbing, on top of these basic facilities, is to create a space where you can reasonably do things in parallel. And then, of course, you have to write the code to actually do the things in parallel, which is the parallel execution piece. And eventually, for parallel query, as opposed to for maintenance commands, you're going to need parallel planning. And the idea here is that the first 3 things on this list are stuff that you build it once, then you've got the infrastructure, and then those last 2 things you do over and over again for each new thing you want to parallelize. So getting through that first pile of stuff is sort of a prerequisite for actually being able to parallelize individual things. Yes, David?
Presumably, when you say parallel planning, you're actually talking about just planning on how to execute this in parallel, not actually planning in parallel.
Yeah, I'm not talking about doing the planning in parallel. I'm talking about planning what parallelism to actually do for a particular query. Yeah.
What makes you think the plan is going to be any different? Wouldn't it just be that the elements of the plan are executed in parallel? Why does the planner need to know?
So the question is, why does the planner need to know? The planner needs to know because the planner has to tell the executor what to do. It has to tell the executor, take this part of the plan and run it in a separate process from this other part of the plan. It just has to decide where to put those breakpoints.
I think the presumption was that the individual nodes themselves know
than doing the query not in parallel, then you want to know that so you can pick a parallel plan. If doing the query if the optimal query plan is not, the planner has to know in order to correctly choose between plans, and also to tell the executor exactly which things are we parallelizing in this particular query. How many parallel processes are we using? What is each one going to be responsible for? All that stuff.
And you could see a potential that individual nodes could actually know whether or not they should be running themselves in parallel, I guess.
The planner will have to tell the individual nodes whether to run in parallel, because otherwise they won't know.
Once you get a infrastructure to support sending data between processes, is any of the work that is, I forget what they're called, XC or the distributed versions of Postgres have an API or an infrastructure that where pipelining queries are done that you would follow or want to keep a similar API to so that you can extend this to a distributed environment on its own?
Right, so the question is, does XC or anything else have any tie into this work? Are there APIs or so that we could reuse? I think that there aren't, because I think that the communication within a cluster is going to be fundamentally different than the communication between multiple clusters. Let me actually just move on through the next couple of slides, since I got a slider free on each of these, and then people can ask questions on each slide as we come to the topic, rather than jumping around. So the basic facilities that we've got in 9.4 are dynamic background workers, which means a dynamic shared memory. So dynamic background workers means you can tell the postmaster, please start a process and have it run this function. And behold, the postmaster will start that process and have it run that function. What happens after that is up to you, right? So it's a really low-level facility. And dynamic shared memory, similarly, is you can spin up a dynamic shared memory segment whenever you want, and it will eventually go away. And the "it will eventually go away" part was actually where most of the work went here. Because it turns out, you know, those of us who are used to coding inside the PostgreSQL backend are used to the fact that when, for example, your transaction aborts, all of your resources get released. Well, it turns out, as I found out the hard way, that if you add a whole new kind of resource and you don't write any code to make it automatically go away, it doesn't automatically go away, because it turns out that the transaction abort machine rate is not magic. So that was kind of when I had the wake-up moment that made me realize that I was building really low-level facilities here, and I had to get things like transaction abort, process termination, cluster termination. There's like 3 different levels of making sure we cleaned up dynamic shared memory segments at the appropriate time. And if you got rid of any of them, then you would have leaks. So that was the complicated part of that. But the good news is it's done. In fact, I've already got bug reports on these things. And the great thing about that is that people are using them, right? We barely got 9.4 beta 1 out the door. I think even before beta 1 went out the door, I had bug reports related to these facilities. People don't find bugs in things that they're not using. So even though we are a long way from having real parallelism here, people are latching onto these C APIs, doing stuff with them that's significant enough that they actually care about whether it works, which I think is fantastic. I think that's really fantastic. Part of my goal here was to build the individual pieces of this project in a pluggable way so that they could be used for parallel querying, but they can also be used for other stuff. And at each layer, I'm trying to make that possible. So next is plugging, right? And this is the stuff where it's like, oh gee, I can get a big chunk of undifferentiated bytes that's called a dynamic shared memory segment, but what the hell do I do with it after that, right? And so one option is do whatever you want with it. They're your bytes, have fun. But that's not necessarily an easy programming model to do complex things in. So one of the things I did at 9.4 is I created this concept of the DSM table of contents. We have a similar table of contents, although it's more complex for the main shared memory segment. And the basic idea here is that this provides some dead simple infrastructure so that when you map a dynamic shared memory segment, you can actually do some discovery and figure out what kind of data structures are in there and locate the particular data that you're interested in within the overall dynamic shared memory segment. Several people said on the list that they weren't sure that I got this part right, and they might well be correct, but we won't know until we try it. I think it's pretty good. I think I can see how to use it for a bunch of useful stuff. But you know, as with any of this fundamental infrastructure, and particularly once you get beyond the absolutely most basic stuff that you know you're going to need, there's some room for maneuvering. Another thing that got done in 9.4 is a simple message queuing facility. I mentioned it earlier, SHM_MQ is what it's called. And this is intended to answer the question, how do background work, how do cooperating processes communicate? If you have a background worker that's running and it generates tuples that need to get to another process so that they can be further processed, or if it just errors out and the other back end needs to get that error so that it can decide to stop doing whatever it's doing, or so that it can print the error out, or whatever it's going to do, there has to be some easy way of doing that, and so that's what I invented this for, as a way that you would hopefully be able to send tuples and errors and notices and what other control information you needed to send between the cooperating processes. And then kind of a low-level, this is still kind of a low-level facility. I did get a bug report on this already, so again, somebody is using it, right? The error propagation piece of this is sort of what I think the next thing is here. The idea is that we don't want every person who uses background workers and dynamic shared memory and message queues to have to reinvent their own way of sending error state, for example, from one process to another process. We want to invent some ways of doing that that are somewhat standardized, and people can, if they so choose, just use them. Of course, some people may want to roll their own for whatever reason, and that's fine too. So that's something that I've just begun to work on. I have some ideas about that that I think are promising. We will see how many rotten tomatoes get thrown at me when I post the patch. Another thing that I'm sort of putting in this category of plumbing is a shared memory allocator. This is an idea about which there is considerable skepticism, which is not without some foundation. Indeed, I have some skepticism myself, despite the relatively, actually very large amount of time I've spent trying to figure out how to make this work. At the same time, if you look for other pieces of software out there that do things in parallel that do not have a shared memory allocator, which today we do not, I think that you will find possibly no such projects, and certainly not many that have been as successful as we are. So, you know, I think there's very legitimate concern about how much shared memory allocation it really makes sense to do. How dynamic can you really make this without having the behavior of the system become complex and difficult to understand? How do you reconcile it with the fact that both our main shared memory segment and these dynamic shared memory segments have a size that is fixed when you create it? On some platforms, there actually are ways of growing a dynamic shared memory segment once you've created it. There are tricky problems there, though, as well. I don't really know what the answers to all the questions in this area are, but I do think that there are going to be some things that are really hard to do if you don't have this. So I'm working on it, and we'll see how it turns out. I think someday we'll want other data structures in shared memory too that have common implementations that can be shared by multiple users. For example, a shared hash table. You can use this on the one hand to imagine creating an in-memory data store extension for PostgreSQL that just makes a big hash table on dynamic shared memory and then stores stuff in there and spits it back out. On the other end, you can also imagine doing it, using it for something like the Compose CID hash so that you can actually do writes in multiple backends at the same time and not lose track of your Compose CIDs. But I'm not planning to work on that right away because I think you got to draw the line somewhere.
You initially said for the hash join that the hash table would be static because once it's filled, it's no longer changed. What about hash aggregates? You thought about that?
No, I have not thought about hash aggregates. That is a good example of where the hash table would need to change as you were working your way through. So that would be a good use case.
It actually grows over time.
Yeah. That's very hard. That particular case of an aggregate is very hard to make work because if you run out of memory in your shared memory segment, you have no workable fallback strategy. For sorting, you do, right? If you fill up your shared memory segment that is fixed size, you don't have to worry about trying to grow it or add another one. You can just say, all right, we're switching to an external sort. Obviously, if you are doing an aggregate, you can't say, let's just not read the second half of the data and we'll just emit the results based on the tuples we've got so far.
Well,
I'm really sure that someone would complain
We'll
about that.
create another hash table.
Yeah, it's a comparison. All right. So these are some things that I think are useful. Some of them are done, some of them are not done. There's debate about which ones are useful and to what degree, which is fair. All right, so setting up a parallel environment. What I really mean by this is making a background worker look enough like a regular user backend to do useful work, and specifically making it look enough like the backend that it's cooperating with that caused it to be started for it to do useful work. This is a complex problem. I think that a lot of it can be done by basically copying relevant state, like the user, which database we're connected to, a snapshot to the background worker, using dynamic shared memory as the vehicle for that. Obviously, this is going to be somewhat expensive. So this is why I say I think this kind of parallelism is probably going to be mainly suitable for long-running operations. If it takes 100 milliseconds to copy all of your state over from one backend to another, your query has to, or a query or maintenance operation or whatever has to be long enough running that you really don't care about the fact that it took an extra 100 milliseconds to get things started. If you're doing a 100 millisecond query, you will care. If you're doing a 5-minute index build, you won't care, provided that there is at least some speed up. Useful work doesn't mean everything, right? Getting the background worker to be able to do useful work does not mean that everything that you could do inside the user's actual dedicated backend can be done equally well within the worker. Some operations seem fundamentally unsafe in a parallel context. For example, if you have a user-defined function that's not a security-defined function, and it sets a good, that good value will actually, that change in that good value will persist after that function returns. That is arguably really weird, but it is a good example of behavior where, in a parallel context, I'm not really sure what that means. I can't really make sense in my head of what the semantics of that in a parallel context are, but they'll certainly be different than whatever they are in a single-threaded process. And so you probably don't want to let people do that. Some operations could theoretically be made safe in a parallel context, but we probably won't bother. Madness, you suck. Is that you? No? All right, maybe that's my own fault. I wrote bother. Or else he changed it to bother when I went to that. It's parallel bother, yeah. So a good example of something that I think might not be worth making parallel C, you then expect that you're going to get the random numbers in the same order that you got them the last time you configured that particular C. Well, obviously, if you make parallel background workers, if they each have their own copy of the random state, they're each going to generate that series, which will produce the user visible behavior difference. Whereas if you're running in a single process, then you'll get one sequence, right? Now you could fix this, right? You could provide code that allows the random state that random uses to relocate its state into dynamic shared memory and build all this plumbing so that this works exactly the same way or enough like the same way in a parallel context that maybe nobody would care. I can't imagine we're going to bother. Maybe you can't even make it safe, but even if you can, who cares? defined function that somebody has loaded into the back end via .so, or even some built-in function that some hacker wrote and put in there, you can't inspect the code of that function and see whether it uses a back-end private piece of persistent state that needs to be copied from one back-end to another. There's just no way of doing that. So I don't see a way around the need to have some kind of labeling of functions to say that these functions are parallel safe, these functions are not parallel safe. If you label your function parallel safe when it's really not, that's your problem. And the planner will have to look over the query tree and say, oh, I might have considered parallelizing this, but it contains a function that's not safe in a parallel context, so sorry. Yeah. It'd be great if we had a program that could analyze another program and determine whether that program is safe, but Alan Turing has something to say about that. All right, so what do we actually need to copy? This is my tentative list. Actually, I should say more properly, this is kind of Noah's tentative list because he did a lot of research on what the main things were here. I think we can probably build a basic parallel environment that can do an interesting level of stuff, copying these things. Obviously, we need the background work to have the same notion of user ID and current database as the original backend. It probably needs to have the same values for all the hooks. It probably needs to know what transaction it's in. Maybe you could do some really simple read-only things without too much in this area. You probably need to copy some elements of the transaction state. If it's going to do any database access, it's going to need the same current and active snapshot that you have in the original backend. And if you've got a Congo CID hash, you have to share that too, because otherwise you might not be able to directly read data that has been previously written by your own backend in the same session. I'm watching the reactions of the other hackers in this room as they groan in pain looking at that list. Yeah.
When you said this was a basic read-only, if this would be sufficient for simple read-only stuff, so right now you're not targeting as your first attempt to do anything involves parallel updates, parallel deletes, or anything along those lines?
Correct. For an initial version of this, I'm not trying to target anything that involves parallel update or delete. Those things are obviously valuable. Be nice to have them eventually. It doesn't seem absolutely essential for the first go around.
Don't you need to synchronize logs to some extent? For example, if you do parallel vacuum and you do reindexes.
I have a separate slide on all this.
Okay.
You haven't said yet whether you're doing writes.
Writes, I'm thinking probably not in the initial cut of this, because if you have writes, then the Congo CID hash can't just be copied. It's got to actually be a shared hash table. And I'm pretty sure there's a bunch of other stuff that is going to need to be fixed as well. This is hard enough, so I want to get this done, and then we'll look at extending. Okay. Now, you also need to prohibit some things. A lot of these things are things that could theoretically be allowed if you have the right state in your dynamic shared memory, but you probably won't. Some of them are things that probably just can't ever begin to work. Basically, these are a bunch of things, again, this is research by Noah, that have backend local state associated with them. Sequences have a backend local sequence cache. Cursor operations, the position of the cursor is backend local. Large objects have cursors. Listen and notify have associated backend local state. Temporary buffers are stored in backend private memory. Prepared statements are stored in backend private memory. Some of this stuff could be synchronized, but it seems okay to me for the first cut of this to say, well, you just can't do those things in parallel context. And we'll figure out later which of those restrictions actually rub on people really badly and see if there's a reasonable way of relaxing them. Assuming I don't die first. Generation of invalidation messages seems like something that can probably never work. I think it's really only going to be an issue if you have like one one user-defined function that's going to create a table, and then another function that gets called later in the same query is going to try to read from that table, or something like that. If those two operations are actually happening in different backends, then the validation messages from the first backend that created the table would have to somehow be immediately perceived by the other backend in time to read the table. It's a mess. I don't want to go there. I don't care about that use case. You probably don't either. It needs to not crash. Lock management is a whole other kettle of fish. This is what Andres was asking about. For the most part, the system overall, I think, doesn't really need to care that much about the fact that a group of processes are cooperating to do something. Most of the data structures that we have in shared memory really don't need to worry about that. Like, the processes themselves need to know that they're doing it and they need to coordinate with each other, but the system overall doesn't really need to know. But locks are an exception. You can think about a couple of ways to try to handle this, and they don't work. The background workers can't take no locks at all and just rely on the user backend to hold the locks, because the user backend might die or be killed before the background worker finishes doing whatever it's doing that requires that lock. That will be a disaster. You could try to fix that by saying the user backend is never allowed to die and release its locks until all of the other workers are dead, and I have no faith at all that kind of solution can be made robust. Another problem, now the other obvious option is, well, the user backend takes the locks initially, and the background workers just also take locks on those things. The problem with that is that parallel query might self-deadlock. The user backend locks some relation with, say, an access share lock. Another process comes along and tries to start a cluster operation on that table, which means no more locks on that table can be granted. Then the background worker comes along and tries to acquire its lock on that relation, and that background worker is now just going to sit there until the cluster completes, which it won't, because the cluster can't start, because the main backend is already holding the lock on that relation, which is not going to release until the background worker finishes working, which is not going to happen because it's waiting for the lock. Okay, so something obviously needs to be done about this problem. One option is just sort of have the background workers try to grab all of the locks without blocking, and if any of them fail, then they just die and you fall back to not parallel query or something. But I think that's a pretty unappealing option, and I think it will be as complex to implement as what I think the real solution here, which is probably have some kind of concept of locking groups inside the lock manager, so that we can say that a group of backends are sharing their lock state. Either they all collectively hold whatever locks they hold, and individual processes acquire or release locks on behalf of the group, or maybe there's some way where we just tell the deadlock checker and related chain rate that processes in the same locking group are allowed to queue jump, and they don't have to wait for other unrelated locks in order to get their own locks. I haven't figured out the details here yet, but I'm sure it will be exciting. Does that answer your question, Andres?
I think there are some additional issues, but we can go into that whenever that comes up.
All right, well, go to the additional issues at the appropriate time. Okay. So parallel execution. In some sense, this is the easy part. I think if you've got all of that plumbing and all of that state synchronization code and prohibited things that aren't saved and all that kind of stuff, and now you've got your basic infrastructure in place, you've got the tools that you need to actually build a parallel algorithm. Well, the parallel algorithms are pretty well described in the literature. They just assume you're using threads and you can just go to do easy locking primitives. Parallel sorting algorithms are described in the literature. They're pretty well understood. You can go read about how parallel quicksort works, or for parallel sequential scan. You hardly even need to think about what to do there too much. It's not. There's a couple of different things you can do in terms of how you interleave the different workers, but it's fundamentally, I think, not that complicated. The major thing that I think that comes up here that's a little bit subtle is Amdahl's law, which says if alpha is the fraction of running time a program spends executing serially, the maximum speed up for parallelism, if you have infinite infinite workers is 1 over alpha. In other words, any time that your background workers spend not being busy is really bad. It will rapidly erode all of the gains that you got from parallelism. If 10% of the time is spent executing serially, you can't get more than 10 times faster. And you can only get 10 times faster if you squish everything else down to 0. So one of the key things that comes up with these parallel algorithms is that you've got to structure the algorithm in such a way that you won't have workers starving because they don't have anything to do. So for example, a sequential scan, you do not want to break the relation into equal-sized chunks and have one background worker scan each chunk. Because then if one chunk turns out to be fast to scan because it's in memory, and another chunk turns out to be slow to scan because it's out on disk, you'll have some background workers that are done, and other background workers that still have lots of work left to do won't really get as much benefit out of parallelism as you could have gotten. You'll probably also have lots of crappy random I/O behavior if you do that. What you probably want to do instead is have the backends kind of work together, work their way through the relations together, so that so first of all, so you get sequential I/O behavior, and also so that you don't have one way ahead of the other.
You might cut out.
My mic died.
Yeah, I'm almost done. I got like 2 slides left.
So parallel query. I said to Noah one time, there are 2 kinds of PostgreSQL development projects. Those that don't touch the query planner and those that are successful. That's a slight exaggeration, but not that much. This is one of the reasons why I think making maintenance operations parallel might be a good place to start. One of the problems that someone in the audience asked about earlier is that you might have a plan that's cheaper for you, and that you'll wait some time to get the results, but enormously more expensive in terms of the expenditure of overall system resources. So we're going to have to think a little bit about what it means to pick the cheapest possible plan. How do we factor in the overall cost of the system and getting up a bunch of workers? And there's other things we'll need to do. We'll need to have a notion of the worker startup costs and the IPC costs that are introduced when you parallelize things. And that is actually pretty much all I have. So I'll stop here and